students. Welcome, virtual students. Here we go. Simplifying some radicals. So the first one, you got really two different ways to go. You could multiply these two numbers together first and get a large number and then reduce it. That's probably the more difficult way. The simpler way is to take each of the individual numbers, like square root of 18, square root of 24, and simplify them and then bring them together at the end. Okay? Couple things to remind you of. You want to treat radicals like they're variables. Okay, that will help you as you approach this. All right, so here we go. Let me focus in just a little bit. Square root of 18 is actually the square root of 9 and the square root of 2, which is 3 radical 2. Okay, so that simplifies the square root of 18. We're multiplying that by, all right, we want factors of 24. 12 and 2 are factors, but they're not the factors that we want. 8 and 3 are factors, but they're not the factors that we want, because we want factors which are perfect roots. What are perfect roots? 4, 9, 16, 25. Remember? We went through all those. 2 squared, 3 squared, 4 squared, 5 squared, 6. Those are perfect roots. So what's a factor that's a perfect root that goes in 24? Well, 4. So square root of 4 and square root of 6. That's what we want to use on that one. And so the square root of 4 is 2. And the square root of 6 is just that. And so now we have that simplified. There are no roots that are factors of 2, perfect roots. There are no perfect roots which are factors of 6. And so now we would just multiply across. 3 times 2 out in front of the radical gives me 6. Square root of 2 and square root of 6 gives me square root of 12. Remember, we treat it like a variable. If I would have 3x times 2y, I would end up with 6xy. Multiply everything together. Okay, same concept. These are literally like coefficients in front of a variable. All right, so 3 times 2 gives us 6. Now, we're not quite done because the square root of 12 still has a factor that's a perfect root. The square root of 4 and the square root of 3. So we'd have 6 times 2 times the square root of 3, 13. And 6 times 2 is 12 radical 3 by a show of hands. Who got that one right? Anyone? Anyone? Couple people? Okay. Those of you that missed, do you see what you did wrong? All right. We got to get better at this. We're simplifying it all the way down. All right. Let's go to number 2. I'll move it to the top of the screen so you can see it. You know, on this one, this looks more difficult than it is. When you multiply those two terms together, you get 225 or you get 15. Anytime you multiply a number by itself in radical, watch. Square root of 3 times square root of 3. That is the square root of 9, which is 3. So can you just jump to that? Sure. So square root of 5 times square root of 5. Square root of 25, which is 5. You see that? So it works every time, no matter what the number is. The square root of 158 times the square root of 158. Guess what it is? 158. It works every time. You see that? All right, so now let's apply it here. The square root of 15 times square root of 15 is 15. So we have 3 times 15, and we still have the square root of 8. Okay? Now, the square root of 3 times 15 is 45. The square root of 8 can be factored to the square root of 4 and the square root of 2. The square root of 4 is 2. So 45 times 2 times the square root of 2, and we have 90 square root of 2. By show of hands, who got 90 square root of 2? Anybody? 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 Nobody? All right, let's go to the third one. Separate this into 2 separate fractions because you can't have a radical underneath a fraction, or a fraction underneath a radical. That is not allowed. So now let's take a look. Oh boy, you can't have a radical in the denominator either. So we have to multiply by 1. I know. That's the square root of 12 over square root of 12. But it's still 1. It's just written weird. Okay? So we multiply across. We have the square root of 60. And we multiply across here, and we have 12. We actually have square root of 144, which is 12. Questions up to this point? We good? Good? All right. Square root of 16 does have a perfect root. That's a factor. The square root of 4 and the square root of 15 over 12. What's the square root of 4? 2. Square root of 15 over 12. The 2 and the 12 can reduce. And so we end up with the square root of 15 over 6. Can the square root of 15 reduce? No. There's no perfect roots that go into it. I can't go square root of 3 and square root of 5 and think I can reduce the 3 and the 6. That don't work because it's underneath the radical. So my final answer is the square root of 15 over 6. Raise a hand if you got it right. Anybody? Boy, we need a lot more practice with the radicals. Okay, so make sure you keep these in your notes and refer back to them. They give you examples of how to simplify. All right, go ahead and get out page 716, 1 through 18. There's a couple problems we want to do on your homework. This homework is due tomorrow, so hopefully you've taken a look at it. Maybe you got done, maybe not. We're going to start off with number 14. Chaz, can you read off number 14? I believe it is, yes.
Each right triangle, find the unknown side, length using Pythagorean if it is possible.
Okay, so each right triangle, if it is possible, find the unknown side. So we know that this is 4 and this is 8. So this is dealing with Pythagorean triples. So are we dealing with SOHCAHTOA? Or are we dealing with special right triangles? No, these are not. These are Pythagorean triples. What were the Pythagorean triples as we discussed? Well, the most common one was 3, 4, and 5. What does that mean? That means 5 squared is equal to 4 squared and 3 squared. Now, let me help you feel better. Okay, so we have 3 squared and 4 squared, which is 9 and 16. 25 is equal to 25. So you see that Pythagorean triple works. Not only does 3, 4, 5 work, but any multiple of 3, 4, 5 would work. 6, 8, 10. 9, 12, 15. Any multiple of those would work. Okay? So then, what we're trying to determine on 14 is, could a Pythagorean triple help us find this unknown side? That's what we're trying to determine. Well, let's set up the Pythagorean theorem. So 8 squared is equal to 4 squared, and then our unknown, we'll call that x. Okay, now, does it fit one of the Pythagorean triples? I'm telling you just from the get-go, it doesn't look like it to me, because it doesn't look like it's a 3, 4, 5. Okay, but I'm going to verify it. So I have 64 is equal to 16 plus x squared. Yeah, this is not going to work. Subtract 16. 48 is equal to x squared. Is 48 a perfect root? Nope. It's 4 radical 3. So we can find the length of the side, but does it fit a Pythagorean triple? It does not. Not possible. So that's my answer to number 14. Does that make sense, Coffee? Coffee. Does that make sense?
Yes.
Okay, let's do number 16. Number 16 says the same idea. We're still dealing with Pythagorean triple. And right triangle XYZ, the hypotenuse XY has a length of 35. Okay, so X, Y, Z, right triangle, this is 35. And then isn't ZY 21? Know what it says? Okay, so if this is a Pythagorean triple, let's look at the ratio, 21 to 35. We don't know what the third ratio is, but let's look at this one first. So 21 to 35, if I reduce that, divide them both by 7, I have 3 to 5. Okay, well, yeah, this is really making sense. Then, if that's 3 to 5 in ratio, then what does the third side have to be? It would be 4. And what would I have to multiply it by? 7. So we'd end up with 28. Everyone see how I solved that using Pythagorean triple? I reduced it. I know that it's a 3, 4, 5 right triangle, the ratio, the proportion. And so the side that's missing is 28. Do you see that? Get it? Okay. You guys want to do number 18 together? All right, let's do 18. Number 1, because I like baseball. Okay? Not because I like you, just because I like baseball. Teasing, jeez. So sensitive. All right, number 18. It says, represent real world problems. A baseball diamond actually forms a square. Okay, let's take a look. So we've got a square that kind of looks like a diamond. Yeah, not too bad. Ish. How far to the nearest yard must the third baseman throw the ball to reach first base? Okay, so I think they want us to say, here's third, and we're going all the way across. Well, they said that it says a square, so that means that these are, well, that means we're dealing with this. A 45, 45, 90 right triangle. Okay, and so if that's the case, how far measuring each side? Measuring 30 yards. Okay, so this is 30 and this is 30, right? And what is unknown? That right there. The hypotenuse. Well, we can use our special right triangles behind Keegan's head over there. We multiply the leg by the square root of 2. So we take 30 times the square root of 2. Well, in a real life problem, we're not going to leave it in radical form, so let's multiply this out. 30 times 2 square root. Oh, whoops. I'm going to have to clear that. Let's go the other way. Let's go second 2 times 30. There we go. 42 point, does it say nearest tenth or anything? Yeah, to the nearest yard. So we'll say 42 yards. That's pretty accurate, right? Aren't the base paths 90 feet or 30 yards? So we'd multiply that by 3. We'd get the number of feet, 126 feet. Now, there's all kinds of little things here. The third baseman doesn't always stand on third base and throw it to first. Sometimes he's, in here a little bit. Or maybe he came in here for a bunt. I don't know. All kinds of things could have happened. But keep it with what the scenario says. All right, any questions on 18? Using a 45, 45, 90. All right, this assignment is due tomorrow, okay? So you've got the rest of the time to finish up the problems today. If you get it done, go ahead and submit it. If you need to go out in the hallway to have good Wi-Fi connection, go ahead and submit it. Okay? But I want you to get it done. Questions? Okay, that's it. Get to work. Virtual students, any questions